Thank you to everyone those who have joined, and we are still waiting for some more people to join. Let's take a few minutes, then I'll start the week 6 of Unsaturated Soil Mechanics tutorial class, and the problem solving class, which will be on demonstration of software for fitting SWCC, solver to characteristic curve, and we'll also discuss about the payload transfer functions. Okay, so as more people will joining, I'll start now. This is the week 6 of problem solving session for unsaturated soil mechanics, and this course is offered by Professor T.V. Bharat from IIT Guwahati, and I'm a PMRF teaching assistant. Mr. Satyam Tiwari from IIT Dhanbad. So the week 6 will be discussing about we'll demonstrate the software for fitting SWCC, so Alberta characteristic curve. We'll also discuss about the Peter transfer function. Okay. So before we get into the content of week 6, we'll discuss one of the problem which we left in the last class. That is of week 3 class. And so the problem states that there are a few water droplets. These droplets are there in a container, and this container is kept at a room temperature. So last class we were not having the data regarding the temperature, but this class we are going to solve it for the room temperature. That's say 25 degrees Celsius. Okay. So as shown in figure 3.13, there are water droplets with initially different sizes, ranging from 10 to the power minus 5 to 10 to the power minus 8 meter. They are in a container, and that actually sustains ambient relative humidity of 101 degrees. So the relative humidity inside the container is 101%. Okay. And we need to determine what will be the final size of the droplets at equilibrium. Okay. So, okay, so let me just erase this one and let's get the pen. So in this problem, what we know here is that the relative humidity, if we write, that's going to be 1.01 or 101%. And the temperature which that is here is 25 degrees Celsius. If we convert into Kelvin, then it's going to be 273.2. And it will be 25 plus 273.2. That's going to be 298.2 Kelvin, right? And now we need to determine that what will be the size of these water droplets at equilibrium. Okay. So here in this equation, if we'll see the RH that determines the vapor pressure, and the vapor pressure at uh, equilibrium is equal to exponential of minus 2 times the surface tension and the dynamic viscosity of water cos of alpha divided by r small r, that is the radius, capital R and T. Fine. So in this equation, the only unknown is R. Okay. We know the value of gas constant, the temperature, the surface tension, the viscosity, and cos alpha we are assuming to be 1 as alpha is 0. Okay. So what we are going to do is that we are going to solve this equation. The relative humidity is given as 1.01. We are going to solve this equation to determine what will be the size of the particle at equilibrium. Okay. So we'll write 1.01 is equal to exponential minus 2 times the value of Ts is given at 72 millinewton per meter. So 72 into 10 to the power minus 3 Newton per meter multiply nu W is 0.018, that's in millimeter cube per kilomole. So we'll convert into mole, and that should be minus 10 to the power minus 3 here also. And cos alpha is 1 divided by small r is unknown. And the value of capital R here is 8.31432, right? And that is joule mole Kelvin. Multiply the temperature in Kelvin, 298.2 Kelvin, right? So here everything is known except R. So what we'll do is that we'll take natural logarithm on both sides. So it will be ln 1.01. Ln and exponential will cancel out. So it will be minus 2 into 72 into 0.018 multiplied 10 to the power minus 6. It divides R into 8.31432 multiply 298.2. Okay. So if we solve it further, then we'll bring R this side. So R will be equal to minus 2 into 72 into 0.018 10 to the power minus 6. That will be divided by ln 1.01 multiply 8.31432 298.2. Okay, all the units are in meter, so that will be in meter. So if we solve it, the value of R will be 2 into 72 multiply 0.018 into 10 to the power minus 6, and we'll divide it with ln 1.01 multiply 8.31432 multiply 298.2. So if we'll solve this, we'll get a value of 1.05 multiplied 10 to the power minus 7. Okay, that's in meter. So we can approximately write is a 10 to the power minus, that's going to be 1. So it's a 10 to the power minus 7 meter. So we can say that at equilibrium, the size of the particles will be 10 to the power minus 7 meter at room temperature, right? So this is the one of the numerical which we left, and now here we get the value of the radius of the particle, which will be there at equilibrium will be 10 to the minus 7 meter. Okay. So if you have any doubt in this one, please let me know. Okay, so we'll move on to the content of week 6. Okay, and previously in week 5, we have discussed there are several models which are used to predict the soil water characteristic curve. Okay, so regarding if you have the data from the laboratory regarding the volumetric water content versus metric suction or head, then in that case, this curve will be like this. And if we have the data from the laboratory, okay, then we can use these prediction model to obtain this curve, or we can best fit this curve to better fit these results from the laboratory. Okay, so one of the methods for the prediction is given by Brooks and Corey in 1964, as we have discussed that up to the point where air entry starts, the air entry point is if we draw two straight lines, that will be here somewhere. So this is the point where the air entry will start. That is called the bubbling pressure point. Okay. So up to that point, it is said that the value of theta or the volumetric water content is going to be equal to saturated water content. Okay. And after the point of boiling or the point of air entry, the function which is given by Brooks and Corey is the value of water content will be equal to theta retention, theta r, and that is the residual volumetric water content plus theta s minus theta r. Okay, so what volumetric water content at saturation minus the residual water content. Okay, and then we'll have this term that will be the bubbling pressure divided by the metric suction to the power lambda. Okay, so lambda is the pore size distribution factor. Okay, so this equation can be used to fit a curve in the laboratory, the experimental data, and this is one of the prediction model which is available from the literature. Okay, and the problem with this model is that it does not obtain a smooth function, as you'll see that. Up to the bubbling point, it is showing the value as theta s. Okay, and after that, the expression is given. So this point, it is not continuous at this point because you'll see the break at the bubbling point. Okay, bubbling pressure. So we'll solve a numerical on this. We have already solved one numerical using the Excel program by fitting a curve in the data as we have seen in the last class. And today we'll see a comparative example of all the mainly three models which we have discussed. Okay, so the second model is Van Vention model that is given in 1980, and this provides the expression for this bigger theta, that is the relative volumetric water content. Okay, theta minus theta R, theta minus theta residual water content, theta saturation minus theta R, and we can also write the Brooks and Corey equation in the similar form, in the form of capital theta. That is the relative volumetric water content. Okay, and or the normalized water content as written here. And in the Van Ginchen model, we can see there is only one expression that is provided. So Van Ginchen model can be considered as a continuous function. So in this model, we'll have 1 upon 1 plus a psi to the power n to the whole power m. So here you'll see there are three terms a and m that are called the fitting parameters. These parameters can be varied while we fit data into the experimental model. Based on that, we will obtain a particular value of a, n, and m that will fit better or the best the experimental data, right? So the value of m is having two expression, M is dependent, M can be written as 1 minus 1 by n in the constraint problems, or when M is dependent on n. Or it can also be said that M is equal to 1 minus 1 by 2m. Okay. So for the when Vinchen problem is when Vinchen formulation is used with mu lem expression, then it is M value is written as 1 minus 1 upon n. Okay. And when Vinchen is used with Burden model, then M is written as 1 minus 1 upon 2m. Okay. These things are discussed in theoretical class. Okay. So for better detail, you can refer to that. So the advantage of Van Ginchen model is that, as we have seen in Brooks and Corey model, there are two expressions, so it is not a continuous function, right? It breaks at psi b. But in the Van Ginchen model, only one expression is provided, so it is a continuous function. Okay, so a smooth transition is obtained at air entry pressure. Okay, and after that, this also allows a greater flexibility than this Brooks and Corey model, and because can be applied to a wider range of suction. Okay, and now we'll move on to the third model, which we have also discussed in the last class, that is Ferdinand and Zing model. Okay. So in the Ferdinand and Zing model, the volumetric water content theta is described as a function C multiplied by the saturated volumetric water content 1 upon this expression. Okay. So here also you'll see there are three fitting parameters A and M. Okay. A, N, and M. Okay. This parameter C is further defined as 1 minus expression ln 1 plus psi upon psi r and ln 1 plus 10 to the power 6 upon psi r. Okay, and this is called a correction factor. So there are three models for the prediction of soil water characteristic curve. The first one is BC model, okay, Brooks and Corey model. The second one is VC model, the VG model, okay, that is Van Ginchen model, and the third one which we are discussing is Verlen and Zing model, right? So now, as we have discussed, three model will solve one problem. We'll use the software Excel, MS Excel for solving this. In this problem, it is written that table 12.2 and 12.3, this one and this one, shows soil water characteristic curve data for silty loam and glacial till. So this one is for silty loam and this one is for glacial till, respectively. So we need to model and compare the SWCC for each soil using Brooks and Corey method, Van Ginchen method, and Friedland and Zing method. Okay, so all three method which we have seen, we need to model these data using these three methods. Okay, so what we'll do, we'll solve this problem for one set of experimental data, and then the second set of experimental data you can solve it on your own. Okay, so if you people are having access to MS Excel, then I'll kindly request you to please solve along with me. Okay? That will give you a better exposure. Okay, so let me reshare my screen so that I can switch to Excel. So here, let me zoom in. So here you'll see the first set of readings are provided here. Let me get it checked from our question. So here the values of the suction pressure UA minus UW, the values of the suction pressure UA minus UW in KP is provided, and then the volumetric water content theta is provided. Similarly for glacier till also. So these values of the for silty loam we have noted down in the Excel. Okay, now we will solve it for three predictive models which we have discussed. Okay, so let's see it for the first model, that is Brooks and Corey model. So the values of suction are provided in this column. The observed values of theta, that is volumetric water content, are provided here. Okay. And then we need to use this expression to predict the values of theta only. Okay. So let's see here the expression for theta is provided as theta r plus theta s minus theta r psi b upon psi to the whole power lambda. The values which are the fitting parameters here are not the fitting parameter. The first parameter is lambda. The second parameter which is there is bubbling pressure, and the third one is theta r. These three parameters can vary to better fit the curve. Okay, and theta s is there. That if you'll see here, then you can observe point 0.1, point 0.2, point 0.3, point 0.4 is around 0.463, which are fixed here. So theta s are fixed to 0.463. Let's say we write 1 for lambda. Okay, for bubbling pressure we write something called 45. Okay, 10, 20, 10. That's going to be around 50 maybe. Okay. We will change these parameters to see what is the effect of these parameters on the curve which we obtain, the predictive curve. Okay, let's write theta to be theta r to be zero point 0.2, just randomly, which we have given these three values. Now we will predict the value of theta from this observation so that we can draw a smooth curve. Okay, that will give you the prediction equation. The prediction equation is already given here, so that will give you the prediction curve. Okay, so here if we see, we can up to the point of phi b, and in this curve if you'll see, if you draw a line here and a line here, then up to this point, that is the point of phi b. Okay, the air entry point, and that corresponds to the volumetric water content of around 0.46. Okay, so from here to here we'll see, we can write this theta is equal to theta s, and the theta s is given as 0.463. We'll fix this value. So for first three expression, we'll write theta as theta s. Okay. Then we'll move on. We will move on to the next, and we'll write the value of theta as this expression. Okay. So it will be equal to theta r, theta r. Let's fix this one, plus in the bracket we'll write theta s minus theta r. Can you let me know at which point we are not getting it? Okay, and then we'll write psi b upon psi, the value which are suction are provided here. So we'll write psi b as bubbling point psi upon this value of psi, which we can write from this point. Okay, we'll fix the value of psi b, and then we'll put power. The power is going to be lambda. Okay, fix this one also. So now if we copy the same formula, then this will give you the prediction curve. So you see the prediction curve from Brooks and Corey is here. But if we properly manage these three parameters, then we'll see that this prediction curve will come a little bit closer to the observed values. These are the observed values of theta versus suction head. Okay, the suction will see, we should say. It's in KPA. Fine, as provided here. So now we'll use a function that is available in Excel that is called solver. So if we go to data and we go to solver, as we have seen in last class, if this function is not activated in your Excel, then you can go to file, you can go to options, and from here you can go to add-ins and go for Excel add-ins. This solver add-in is there. Okay, if you select this one and click OK, it will automatically install in your Excel program. Okay, so you go to this solver program. Now here, what we need to do, okay, we have missed one step, that we need to determine what is the error in the prediction. So the error in the prediction is the predicted value minus observed value. What is the predicted value? The predicted value is this one, okay, minus the observed value of theta is this one. And we need to determine the square of it, okay, so that there is no negative and positive values, only positive values. So here we have determined the observed minus predicted minus observed values here. the square of the predicted minus observed value. Then we'll determine the sum of these squares. So our objective now is to minimize this sum of square because we need to minimize the error between prediction and observed values. Okay, so we will use this solver program to do this. We need to select the objective. Our objective is to minimize this sum of the square value. Okay, and what we need to do, we need to minimize this value. We need to minimize the error. Okay, and what we want to change for minimizing this, we need to change these three parameters. So I'll select for Brooks and Corey model. We will, okay. So for Brooks and Corey model, we will change these three parameters to obtain the minimum point or the most optimum point. Okay. Now if I click solve, it will automatically change the value. See, lambda is changed to 0.89, bubbling pressure 51, psi r is theta r is 0.035 something. So if you now observe the curve, now I'll keep the solver solution and click OK. Now if you observe, this curve is coming from here to here. So now it better fits the values provided in the experimenter. Okay, fine. So similarly, so here what we did, we optimized the values of these three parameters to better obtain the values of the predicted theta. And what was our objective while obtaining predicted theta is that we needed to minimize the squared sum of errors. Okay, the errors are predicted minus observed values. The whole square of the predicted minus observed values. Okay, fine. So this one is the Brooks and Corey model. Okay. So Brooks and Corey model, it's not having a smooth function here because this is a graph plotted by using these value. That's why it's showing a smooth, but it's not actually smooth at this point because we need to provide different function up to here by psi r. Then we need to define different function for rest of it. Okay, fine. So you can let me know when you have finished with the Brooks and Corey. Then we'll move on to the second one. Okay, let's take few minutes before we move on to Van Genchen model. Okay, so now I think we can move on to the second model to fit the prediction curve using Van Genchen function which is provided by Van Genchen. Okay, then for this one, the expression provided is here. Theta, the bigger theta is equal to theta minus theta r upon theta s minus theta r is equal to this function which is here. So the three unknowns or the three parameters, fitting parameters are a and n m. So I've provided a random value. Let's say n is zero point 0.5, the a is zero point 0.5, n is let's say 10, and this one is 0.02. The theta r value, which let's say we have written 0.035 as in earlier case, in this case. Okay, now we'll write the prediction equation. Okay, so the prediction equation is going to be theta is equal to theta r plus theta s minus theta r if we send it in this side. Okay, so that's going to be theta is equal to theta r, fix this one, plus put a bracket, and that's going to be theta s minus theta r, theta s, oh, minus theta r again, We'll close the bracket, multiply. We'll have this function in multiplication. So let's put a bracket, another bracket, 1 upon what is the function here? Put a bracket, 1 plus that's going to be a psi. So the value of a is here, and we'll fix that one. Multiply the value of psi is in the first column here. Then we'll close this one. This will have a power of n. So the value of n is here. We'll fix this one. We'll close the bracket. Okay. And we need to mind the bracket where we need to close. Okay, fine. So we'll close this bracket and the power of this 1 plus this is going to be m. So the value of m is here. Let's close this and we are set. Okay, so it is giving you a value of 0.359 something, and if we copy this through all of this, then we'll get the values of predicted theta. Okay, now if we observe the predicted theta, the predicted values minus the observed values and the square of it for all the values which I have calculated, then this one is the sum of the square errors. Okay, so now again we need to now, if you see the curve here, it's like a straight line and it is not fitting at all. Okay, so now if we change this value, now if we use the this solver program to change the values of a and m and theta r to better obtain these values of predicted theta, so that we can minimize the value of sum of squared error. Then how we can do that is we go to solver. This time we set the objective to this point, Van Ginchen model, sum of squared error. We need to minimize the sum of squared error by using the variables which are given here. Okay, and now if we solve it, that's going to give you our these values, the value of a and m and theta r. Okay, and if we close it, then we'll see this is the curve which has been fitted. Okay, so this is very close with the BC model, just that it is not having a discontinuity at this point. Okay, so if you will observe the error, sum of squared error, then the sum of squared error in BC model is 0.0025, and in here it's 0.00022. Okay, so it has decreased drastically, and right. So this was the Brooks and Corey model. Okay, and this model was Van Ginchen model. Now, the third model which we have discussed is the Friedland and Zing model. Okay, so first we try the Van Gunchen model, then we'll go on to the Friedland and Zing model. For any queries, kindly raise your hand. And here you can see the volumetric water content versus substance graph. Okay, that is WCC. Okay, so let's move on to the next model, that is of redundant zinc model. Okay. In this model, we'll have an additional parameter, that is the correction factor, the value of which is equal to 1 minus ln 1 plus psi upon psi r, ln 1 plus 10 to the power 6 upon psi r. Okay, so for that, we'll first write the values of C pi, or determine the values of C psi. Sorry. So we'll write it here 1 plus, then we'll put a bracket, and another bracket that's going to be numerator, that is ln, the natural logarithm. Okay, the natural logarithm, that's going to be ln. We close the bracket. We'll open the bracket, and it will have 1 plus psi upon psi r. So 1 plus the value of psi will be suction will be here. Okay, upon the value of psi r, that's going to be here. That's going to be q6, and we'll log this value. Okay, then we'll write the denominator part, that will be, add a bracket here also, so that there's no confusion. And now we'll write the denominator part, that is ln. Inside it will have 1 plus, this is 1e6, or 10 to the power 6, divided by psi r. Psi r is here. Let's log this one too, and we'll close the bracket and the bigger bracket. So that's going to be the value of C, instead, value of C for all the observations. And now we move on to the value prediction on the values of theta r, theta. Okay, the volumetric water content. Okay, so let's write the value of theta is provided here, so that will be equal to, first we multiply the correction factor into theta s, which is given here. We'll log this one, and then we'll have a bracket which will have 1 upon the value of ln. Inside is exponential, so we can write exp of 1. Okay, and then we'll have plus another observation, that is psi. The psi is given here, a3. Okay, and divided by a, the factor a, which is provided here. We'll log this one, and if we have to provide the power n to this one, so the n factor is here, logging this one, and we'll close the bracket of ln. Okay, then we'll close this whole bracket. Okay, then we'll have the power equal to m, right? Let's close this one, and okay, let's check the bracket. So here we open the bracket of ln exponential, that's going to be closed here. The bracket of ln exponential, find the bracket of ln is closed here. Then we'll close the value of 1 plus the power something, and that's all. So we don't need this bracket. So these are the predicted values of volumetric water content. Okay, and if we copy this for all the observations, then we can leave this one. This is not observation, so we can write the predicted values of water content here. Okay, now if we'll see the graph of these predicted values, it is showing the best fit, because these values are already the best fit parameters. So let me just change this one. We'll write 50 for this, maybe 4, maybe 0.2. Okay, this one is 0.4 maybe. So now you'll see this curve is going up. Okay, predicted values from redundant zinc model. So again, we need to find what are the errors. So predicted values minus the observed values of theta, then we'll have the square of it. And if we copy this through, then these is the sum of the square error, 0.8788. So how we can decrease this one? We'll again use the solver program. We'll go to solver. We will set the objective function to this sum of squared error this time. Okay, that is going to be O19. And then we'll put the minimum value we want for this objective function. Then the parameters which we are changing are these. So let's solve this and let's see what are the solutions which are obtained. So here you'll see the predicted value of theta from Lensing model is coming like this. So if you observe the sum of the squared error, then here it's going to be 0.000046. So it's a little bit more than 0.0002 from Van Genchen model. So the best fit model which we obtained here is from the Van Genchen. And the least fit is the Brooks and Core model. It is also having a discontinuity. Okay. So now you can try the Fred-Lensing model in your system if you want. And if you are using the Excel program, okay, then you can let me know if you have any problem with that. I'll wait for maybe 5 minutes. And also for plotting this graph, as I can tell you here that for plotting this graph, just plot a line graph that might be line graph or the scatter graph. Then you can go here. You can select your data. Like the first one, for the first one, I have selected the observed values of this theta here. Okay, so you can just edit this one. The observed values of theta are provided. The observed values of for the x-axis I provided the suction values, and for the y values I provided the values of the volumetric water content. Similarly, for all the prediction model for broken core, Van Ginchen model, and the Frontline and Zing model. Okay, so you can just give the x-axis as suction, y-axis as volumetric water content. So that will give you this plot. For the observed value, you have plotted the scatter plot. For other values, I plotted the line graph. Fine. Okay, so let's move on to our slides. And here we discussed. So here we solve this problem using the Excel program and obtain the fitting curve for all three methods which we have been asked to solve from. So Vixen Core, Van Genchen model, and the Fredland and Zing model. Okay. For the glacial till soil, you can also try at home that how are the curves which you are observing. Okay. So for this one, you can observe by your own. So, as we've discussed in the last class, that there are two types of curve. The first one is the solver rate characteristic curve, for which we have learned about several prediction equations, prediction models. Okay. Now we have hydraulic conductivity curves also, functions also, which we have seen in the last class. That we have several methods. Some are empirical method like Richard and Gardner method. Some are like statistical methods like Jackson method, Burdin method, Mollem method. Okay, these are used to determine the hydraulic conductivity in unsaturated soils. Okay, and if we see the hydraulic conductivity, then we'll observe that as the volumetric water content increases, this direction, as the volumetric water content increases, the hydraulic conductivity which is there, it also increases, right? And as the volumetric content will increase, the suction value will decrease. So you'll observe that the hydraulic conductivity and the volumetric water content, they have a proportionate relationship. Okay, and the suction value and the hydraulic conductivity, they have a inversely relation. They are inversely related. So as the suction will increase in this direction, the hydraulic conductivity will decrease, right? So here you can see the matrix suction as it is increasing, the hydraulic conductivity it is decreasing. Okay, so so from the theoretical class, which we have studied that how we can use this SWCC curve data to model the infiltration problem, okay, and to model hydraulic conductivity and the flow of water in the unsaturated soil or in the infiltration problem. So for that, if you'll see from the laboratory, we have the data of matrix suction versus theta volumetric water content that is called by SWCC, right? Then from this discrete data, we use several prediction methods like the three methods which we have discussed, the Brooks and Corey method, and Genshin method, Friedland and Zing method, and any other methods. These methods are used to fit a curve, okay, that can give you a smooth curve for the prediction of the volumetric water content based on the values of matrix oxide. Okay, these curves have several parameters, the fitting parameters, which we need to optimize to obtain. Like here it is shown that in the Van Gunchen model we have A, M, and N. In the Berlin model we have A, M, and N. Apart from that, we also have CR, that is a correction factor. These factors need to be optimized to obtain a better fit, a curve which can best represent, which best represents the experimental data, right? So for that, the optimization part, we also use several algorithms. Like we can use linear gradient based algorithms. Okay, gradient based optimization. We can also use some other optimization like particle sound algorithms. Okay, we can and other natural inspired algorithms for optimization problem. Okay, so the second part is like AI and ML part, where we'll be using natural inspired algorithms for optimizing these parameters. Okay, and mostly will be focused on this linear gradient based optimization methods. Then, when we'll obtain the best fit curve after optimizing the parameters, the fitting parameters, then we can use the statistical models. These models can be from Burdin, Mollem, Kong model, etc. As we have seen in this slide, Burdin model, Jackson model, Mollem model. These models can be used to obtain the relative hydraulic conductivity or the hydraulic conductivity based on the metric suction value. Okay, so from this curve, we can jump to this curve using statistical models. And then these hydraulic conductivity data, the change in hydraulic conductivity with matrix suction, this data can be used for the modeling purpose for the infiltration problem. So for modeling the infiltration problem, what we need? We need a soil water characteristic curve data, okay, from laboratory, right? So while discussing about the optimization technique, as I've mentioned earlier, that we can use gradient-based optimization. So stochastic gradient-based descendant of optimization, in which if we are going from higher gradient to the low this minimum point, then either you can go like this, okay. But mostly in gradient descendant optimization method, if we are starting from here, then we'll go here, 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 and then we'll follow this path to the minima, the global minima, right? And sometimes these algorithms have disadvantage that they trap in local minimum values. So let's say here this is a local minimum. Ball starts from here. This might be trapped here and think it as a global maximum, global minimum. But actual global minima is here. So these are the disadvantage of these linear gradient based algorithm. They sometimes trap in local minimum, right? To mitigate these problems, we take help of the other optimization methods, such as naturally inspired optimization algorithms, as we have studied in the theoretical class, genetic algorithms, and colony optimization, particle swarm optimization, B algorithms, etc. Okay, so they are inspired by nature. That genetic algorithm they based on the genetic behavior which is there in humans and which is there in the genes, and the ant colony optimization, that how ants follow a particular path, and the path which is longest they do not follow that like that. So we also have particle swarm optimization algorithm and B algorithms. There are several other algorithm, nature inspired algorithm, that are used for the optimization. So for this process flow which I have shown here, from SWCC to obtaining the relative hydraulic conductivity and the optimization of the prediction curve, we will learn about one software, that is the software RETC software. Okay, it is open source software that is given by Van and Gunja in 1991. Okay, and uh, open source software which is having a several function for the fitting Van Gunja methods and BC model, etc. So we'll be using this software and we'll learn how to use it. Okay, so before that, I will give you a short intro on how to install this software in your system. Okay, so the name of the software is RETC. Okay, so you can simply go to your Google or Mozilla, whatever browser you are using. Okay, going here, you can search here RETC, and or you can directly go to PC Progress website. Okay, so when you go to your PC Progress website, you'll see the RETC download. Okay, so these are the RETC installation versions. So you can download any version as per your will. So 6.01 if you download the latest version. So you might they might ask you to, like, I have logged in here. So they might ask you to log in before downloading this one. So just quickly make an account and download this free software which is open source from here. So it will be downloaded as a extension file, okay, which will it will be download zipped file as extension that will automatically unzip when you'll run it. Okay. So after downloading, the installation process is quite easy. Okay, you can from here you can also get the paper and manual. If you go to support, this is from Hydras, programs, news, home. Okay, so where is RETC? If you see here, there it is, RETC. So here you'll see the author. This is a reference. From here you can get the PDF of this particular report, from where you can learn more about the RETC. And this convention paper also you can download from here. It will show you the system requirements and etc. So you can also join the RTC discussion forum, etc. So there are several things which we can explore in this website. And after that, you can install the RETC code or the RETC software, which is quite easy to use. So we'll shortly demonstrate how to use that for problem solving. And we'll solve this problem using that code, that software. So let's take a 10-minute break before we do that. Okay. In between that, you can try the problems and let me know if you have any doubts. So let's start from here, and we are discussing that how we can use RETC code of the software for the determinant for solving this problem using the values of metric suction and volumetric water content till determining the hydraulic conductivity of the sandy soil. Okay, so here in this example, this table shows us to CC and hydraulic conductivity function data of sandy soil, and and then we need to model this using Van Gunchen function. So now here we are not going to use Excel, but we are going to use the software that is RETC code or the software. Okay, and then we'll optimize this parameter. We can use this model which m is equal to 1 minus n constant. Okay, that is the Van Gunchen model along with Euler model. Okay, so let's see how we can solve it. We'll switch to the software. This is RETC software which I've already pre-installed. And if you open it here, this is one of the problem I was working. This is the interface of RETC, and you need to go here and click on a new project. Then you can give it a name, maybe NPTEL one, and we'll write the description. That's going to be week 6. Let's say week 6 only, and click OK. Okay. Then there are two set of windows you'll see here. First one is for uh, pre-processing data which is needed, and second one is for post-processing. So it's quite simple. So if you see here, the first one is the type of the problem. Okay. So you go here and click on the type of problem. So it will ask you that what type of fitting you want to do. So what type of data do you have? Okay, so let me check who is there. So it will ask you that what type of data do you have. So I will have the data of retention data. Okay, that is the volumetric water content and the suction values. Okay, or the pressure values. So I'll click OK here. Then the second set of values which are of scale unit. So what type of unit which you are using. So if we switch to our problem here, then here the values are in kPa, kilometer per meter square, and the values of theta. Okay, so here we can write that we can use the values in all in SI units, so meter and second, right? These information about the iterations which will leave as default. Okay, now if we click OK, then we go to our next set of input, that is the type of retention curve model you want to use and the conductivity model which you want to use. So the Van Gunchen model with variable m and n can be combined with Nolan model. Then where m and n both are variable, then you can also combine it with burden model for conductivity. And the Van Gunchen model with this constant of m is equal to 1 minus 1 upon n. Okay. And with Newellem and Van Gunchen 1 minus 2 upon n with burden. Then you have Brooks and Corey model here, log normal distribution and dual porosity model. Okay, so all the model which are available here, we don't have the model of Redline and Zing here. Okay, so here we are supposed to solve using this convention where m is equal to 1 minus 1 upon n. Okay, now we go to our problem statement and we see how many data points we have. 1, 2, 3, 7, 8, 9, 10, 11, 12 data points we have. Okay, so here we will let's go to the software. Okay, I'll open them. So convention model. Let's click OK, and okay. Here we can write how many number of retention data we have. So we have 12. So just revise it to 12. Then we click on hydraulic conductivity, soil hydraulic parameters. So the parameters which are ticked here, which we need to be fitted, okay. But here we want to fit. We don't want to fit several parameters. So how these parameters are selected? That you select the type of the soil and approximately, and based on that, it will select the parameters. Okay. Then these parameters will be optimized to better fit the curve. Okay. So here we are selecting the silty loam if it's available. Silty loam. So these are the parameters for that. Okay. So here we had a sandy soil. Okay, so we'll select the parameters for sandy soil. So let's come here and we'll click on sand. These are the parameters. What parameters we need to optimize? We'll optimize theta R, theta S. So maybe we don't need to optimize theta S, then we can click here. Okay. If you have the values of theta S, so here for now, I'll leave all the values for the optimization for the fitting. Okay. If you click OK, then you can go to the retention curve data. So here you'll have to input the values of pressure and the values of theta, volumetric water content, and if any weights are there to be assigned this particular set of data. Okay. So now we can write down our values here. Let's see. So let's search for the values which we need to write. Let's see. So retention curve data for the pressure value will write 0 0.1. The next one is 4.47, 9.5, then 14.71, 20, 26.15, then we'll have 36.96, 44.93, 62.34, 96.06, 195 and 789 7843. Fine. Then we'll write the values of theta. So it's going to be 0 0.5 here, the third set, 0 0.49, 0 0.46, 0 0.42, 0.38, 0.34, 0.3, 0.26, 0.18, 0.14 and 0.11. Okay, so we have written the values of pressure and theta. We can leave the weights as nothing because we are not assigning any weight to anything. So it will automatically assign one weight to all. Okay, if we click OK, we go on this software, and now if you come here to again retention curve data and we click on next, then it will ask, do you want to save the input data? We'll say yes. And do you want to run the RETC application? We'll click on OK. Then a command window will open. And then it will ask you to press enter to continue. As you enter, you can see in the post processing, you have two outputs. First one is the graph. Okay. So in the horizontal variable, we want the pressure head. Okay, that's nothing but suction. In the vertical variable, maybe we want the hydraulic conductivity. Okay, so if you like to write pressure head in the vertical direction, let's say we want water contents. So here you can see the data, and if you content, if we change it to the log of pressure head, then this curve is obtained. These are the values which we have provided. This is the best fit curve here. So it is fitting very well. Okay. Now in the vertical axis, we can also get the hydraulic conductivity. So this curve will look like this. Okay. And the hydraulic capacity, we can change the variables in the vertical and horizontal axis to see the curves which are available here. Okay. Then we also have the second file, which will tell you that what are the optimum values of these parameters which you have fitted, and it will also tell you the what are the outputs based on the these are the number of iterations. Based on that, what's the value of sq theta r, theta s, or how it is changing, and you'll see here after fourth iteration, it will just value of SSQ is almost the same. Okay. And here also you can observe it's going to be same after a particular number of iterations. Then we can find the correlation matrix. Okay. We can get the observed and fitted data here. Okay. Soil hydraulic properties we can obtain from here. Okay. So all the properties which are there, which we are plotting in the graph. So this is how the software work. You for exploring more, you can go onto help menu and use the help command from here, or you can download the RTC manual and use that. So we have seen that this is a very simple software that will give you a best fit curve Okay, or you can do it on Excel also. Okay, but this one is open source software, so you should surely explore this one. So based on that, we'll observe these curves of metric suction versus volumetric water content, okay, and relative hydraulic conductivity versus metric suction. Fine. From the data, you can obtain it easily. Okay. Now we are moving on to the another another method here, that is Arya-Paris method. In this Arya-Paris method, there is a Pedo transfer function, which here it is given in 1981, and this function is used to directly find out the SWCC from grain size distribution curve data. So if the grain size distribution curve data of a particular soil is a particular material is available here, soil, and then from this we can obtain the SWCC curve data. Because if you'll see here, if the grain size distribution curve data and the SWCC curve data, they almost have a almost show the similar behavior. Okay, so the Arya-Paris method provides you with the number of formulation or number of steps by which you can get the SWCC curve data, SWCC curve from the grain size distribution curve data. Okay, so this is a particular grain size distribution curve data, that is percentage final versus grain size. And in the RFRS method, we divide this grain size distribution curve data in several segments. This division is based on the data points which are available here. Okay. And based on these divisions, number of divisions, we use RFRS method to find out the suction head or the HWCC curve. Okay, so how we can do that? We'll have a look at the method here. So these slides are taken from theoretical classes where you have already studied. So I'll just quickly go through it, and you'll see in the Arya-Paris method, we first determine the volumetric water content, determine the pore water ratio, the void ratio, sorry, from the values of rho s, okay, density of soil solid, and the rho d value, okay, density of dry soil. From these value we obtain the value of void ratio. Okay, so as we know that rho d is equal to rho s upon 1 plus e from this formulation, then if we rewrite this expression, then it will give you e is equal to rho s minus rho d upon rho d. Fine. So this expression is nothing but the expression between void ratio and densities. Then from this void ratio data, we will obtain this this volumetric pore volume, okay, at pore volume at every section. Okay, for that we will need, this will be given by the formula vi is equal to mi into void ratio upon rho s. The value of mi is mass fraction, so it is the solid mass fraction per unit sample of the mass in the ith segment. Okay, so for obtaining that one, we will what will the formulation which we'll use here is the fraction which is there in ni plus 1 minus fraction which is there in ni, and we'll divide it by 100. Okay, so that will give you that how much fraction of mass is available in a particular segment. Okay, so this ni plus 1 ni, okay, and if we divide that by 100, then it will give you how much fraction is available here, right? This side ni plus 1. Fine. So with this, if we can obtain this pore volume at every section, then we can also obtain the volumetric water content using the relationship between volumetric and gravimetric water content. So for that, what we'll do, using this relationship, that is between the volumetric water content and the pore volume divided by the bulk volume. So using this formulation, we can determine the value of volumetric water content. For a unit mass, the value of we can determine this VB can be determined as 1 by rho d. Then in the fourth step, we will need to determine the pore radius. Okay, that core radius will be equal to Ri into this function. That is the empirical formulation. There, alpha is a model parameter which ranges from 1.1 to 1.4. Okay, and the value of number of particles can be determined from this mass fraction divided by the volume of a particular spherical particle in that range. The value of I is actually the average of the particle diameter or the particle radius, right? Ri plus 1 divided by 2, right? So with the data of Ri, that is core radius data, we can go further to determine the suction head or the suction is equal to pi ts cos alpha upon Ri. Cos alpha is usually taken as 1 because the value of alpha is 0 mostly for the soil. Okay. So we will use this RA-Paris method to solve one example that is given here. Okay, you might also have solved this in the theoretical class. So in this example, the value of GS is given as 2.67. The dry density rho D is given as 1.4 gram per centimeter cube. And we can determine the saturated density by GS into the density of water. So it's going to be 2.67 gram per centimeter cube. The density of water is 1 gram per centimeter cube. Okay. And for a particular section, it is given that Ni plus 1 is 11.866. Okay. This one. And the Ni is given as 10. So for the first section, it is given like that. So how we can use this method? Let me get the formulation with me. Okay. So here, as we know the value, the value of GS is given as 2.67. The value of rho D is provided as 1.4 gram per centimeter cube. Okay. The value of Ni plus 1 is 11.866. Then the value of Ni is given as 10, right? For a particular set of particular for the first segment, if you can say. So here we can determine rho s, that's going to be Gs gamma W. It will be equal to 2.67 into 1, 2.67 gram per centimeter cube. Then we can use the first formulation that is provided for E. It is equal to rho s minus rho D divided by rho D. So it will be equal to 2.67 minus 1.4 divided by 1.4. It will give you a value of, let's find it out, 2.67 minus 1.4 divided by 1.4. It will give you a value of 0.907. Okay. Then we move on to the second term which we need to determine, that is equal to VVI. The value of VVI will be equal to, if you see the formulation, then it will be mass fraction into void ratio upon mass fraction and void ratio divided by this density of soil solids. So for that, we'll need to determine Mi. So the value of Mi is nothing but Mi plus 1 minus Mi upon 100. So for the first fraction, it's going to be 11.866 minus 10 divided by 100. So that will be 0.01866, right? So 1.86 is 1.866 divided by 10. This is going to be 0.1866, right? And sorry, divided by 100. So it's going to be 0.01866. And if we put this value here, that's going to be 0.01866 multiply the void ratio, which we have obtained 0.907 upon rho s is 2.67. Okay, so if you solve this one, then we are going to get a value of VVI as 6.99 into 10 to the power minus 3 centimeter per cube. Okay, this is for per gram of the soil sample. Okay, the mass of this volume fraction. Okay. Okay, after that, we will need to determine the value of volumetric water content. Then the value of volumetric water content can be determined by the formula theta Vi is equal to summation of J1 to this particular value J is equal to I, which is equal to N VVI upon VB, this bulk volume. Okay, and this VVI we already know. So for first state, it's going to be 0.01866, and the value of VB, as I say, 1 upon rho D. So it's going to be 0.01866 multiply 1.4, but value of rho D is 1.4. So it will give you a value of 0.01866 multiply 1.4. It will give you a value of 0.009, right? Okay, so this value I've written wrong. This is going to be 6.99 into 10 to the power minus 3. This one is the value of MI, not the VBI. Okay. So we have obtained the value of volumetric water content as 0.009 for the first segment. Okay. Then we need to determine the RI value, the radius value, and the soil suction value. So let's take a new page, and here we'll determine the value of that how many number of particles are there first. So, so the number of particles which are okay, number of particles which are there, that's going to be 3 mi upon 4 pi rho s ri cube. Okay, now if we put all the values here, then 3 into the value of mi mass fraction which we have determined was 0.01866 divided by 4 into pi into rho s 2.67 into the value of Ri is the that we can determine from uh, the average radius. Okay, so if we'll see there in the question, then the average radius we can determine by writing. Let's move here to our slide, but if I move, this will be lost. So cancel condition. Okay, so we have a V over here. This. So here, if you'll see, the particle size is 0.001, 0.002 for the first segment. So, so particle size is 0.001 and 0.002. So Ri can be written as 0.001 plus 0.002. That is the diameter. So we'll divide by 2. Then for the average, we'll divide again by 2. So it will come out to be 0.001 plus 0.002 divided by 4. 1 plus 0.002, 7.5 into 10 to the power minus 4. So from this, if we determine the value of Ri, then it will be uh, nothing but Ri into the value of first we'll determine the value of number of particles, then it will be 3 times the value of Mi, that is 0.1866. Okay, and divided by 4 into pi into 2.67 rho s multiply the value of Ri. That's going to be 0.00075 okay, to the power 3. Then if we solve this one, then we'll get the value of Ni as 3 into 0.01866 divided by 4 into pi into 2.67 into 100,075 to the whole cube, and that will give you 3954831.44 particles. Okay, so while determining Ri, we can use the expression Ri is equal to capital Ri into 4 times this void ratio and this Ni number of particles which we have obtained to the power 1 minus alpha upon 6 to the power point 5. The value of Ri we have obtained 0.00075 multiply 4 into the value of void ratio we have obtained earlier 0.907 multiply by this value 394,395,4,831.44, and the value of alpha is given in the question as 1.349, so 1.349, right, divided by 6 to the power 0.5. So after solving this one we obtained Ri as, let me solve this one, 4 into 0.907 multiply 3954831 to the power 1 minus 1.349, and it will be divided by 6 to the power zero point 0.5, and if we multiply it by 0.00075 it will give you the value of our I as 4.117 into 10 to the power minus 5, right? The unit which you are taking is centimeter from starting, so I is also in centimeter. Then after solving this, we will solve for the value of matrix suction. So let's start again. For the matrix suction, it's written twice Ts cos alpha upon Ri. Okay, so twice Ts cos alpha, 2 into the value of Ts is given 72 in uh, millinewton, so that's going to 10 to the power minus 3. We'll convert it to kilonewton, so again multiply 10 to the power minus 3. Cos alpha is 1, and the value of Ri which we have obtained, that we can put here. I think I lost that value while solving. Oh, I have it here. So that's going to be 4.117 into 10 to the power minus 5. So it will give you a suction value of 2 upon answer 72 into 10 to the power minus 6. 3.49 kPa kilopascal. So while solving this one, you need to be careful about the unit. Okay, there might be any mistake I think while solving, so you can check it out again by your own, right? So here in the tutorial, in theory we have obtained 515. Okay. So the motto was to discuss that while solving the problem, we from starting from the particle size distribution, we can reach out to determine the suction value, and we can plot the SWCC curve. So here it is shown from the example that if we plot the SWCC curve, that it approximately it becomes very closer to the measured data. So the RFRS method is very good method for mainly for coarse grain soil, okay, because of some assumptions. Mm. And it also works fine for fine grain soil, but it is well suited for the coarse grain soil. So now we have a question which we can solve. Uh, so here I'll be using the Excel program for solving this one. So here we have the data of particle size and the percentage finer. And then solving for different terms, we can determine the SWCC curve. Let's see how we can do it. Let's move on to Excel and RFIDS method here. So here we can, why I'm using Excel, so that we can do it for all the values from top to bottom, right? Not only for first two observations. So we'll start one by one. So first thing we'll have to do is that we need to fill up this data. So the dry density which is given in this question is, let me get the data from here, which I've already noted and solved the problem. So the dry density given here is 1.4, the GS is 2.7, density of water as we know is 1 gram per centimeter cube, and the soil particle density is 2 point, it's going to be rho s, it's going to be GS into gamma W. So the GS is 2.7 multiply 1, so it's going to be 2.7 in total. And then we can determine the void ratio. As we know the formulation of void ratio, that's going to be rho s minus rho d. So the 2.7 minus 1.4 upon 1.4. So it will be equal to, yeah, 2.7 minus 1.4 upon 1.4. So it will be equal to 0.929 something. And then we can determine the bulk density, that is nothing but for one unit mass, it will be 1 upon rho d. So it's going to be 0.714 centimeter cube per gram. And then we can put the value of alpha. We can assume, we have assumed alpha as 1.4 and the PS value is given 72 millinewton per meter. So now let's come here. First, we determine the mass value. So how we can determine the mass fraction? That's going to be n plus 1 1th term. Let's read the first line. That's going to be n plus 1th term. Okay. And the percentage final here minus the percentage final here. And then we will divide the whole by 100, right? And we can copy this here. So we got the mass fraction values. Then how we can get the volume fraction? That will be equal to mass fraction into E upon rho s. So it's nothing but mass fraction into the void ratio and divided by, let's log the void ratio, and it will be divided by rho s value. So the rho s value is here. So from here we can get the mass fraction values. Now we need to determine the volumetric water content, the formula for which is the summation, that is a cumulative term. So volumetric water content will keep on increasing. So that is summation VVI upon VB. From here you see summation VVI upon VB. So here the VVI term is this one, okay? And then the VB term is this one, which we need to log. Fine. For the second one, it's going to be this plus summation VBI, or this one divided by this VB. Let's log this. If I copy this here, then it will give you the volumetric water content throughout, right? Because it will accumulate. This will be added to this one, this will be added to this one, like that. Then we need to determine the capital RI value. So RI value is nothing but this is given as a diameter. So you write multiply 0.5 into this value, this plus this by taking average particle size and divided by this. So it's going to be 0.048. We can do this for all the values. So we got Ri. Now we need to determine the number of particles. So for that, we'll use the expression that's given by Mi upon, it will be written somewhere here. This one, 3Mi upon 4 pi rho s Ri cube. Okay, so let's write it here. That's going to be 3 multiply Ri is provided in mm as the particle size is in mm. So it's going to be 3 times Mi mass fraction, and that will be divided by a long term, that is 4 into pi into rho s Ri cube. Value of rho s is given here, soil particle density in gram per centimeter cube, and rho s into Ri cube. The value of Ri is in mm. So F3 to the whole cube. Right. We will log M5 And now we need to see what values are in mm and what are in centimeters. So this is in mm, so we will convert it into centimeter. Okay, that will be multiplied by 10 to the power minus 1. Or maybe you can convert this rho as value to gram per meter, gram per mm cube. So we'll just multiply it by 10. So the value of rho as is here, and we can multiply it. We can divide it by 1000. Okay, centimeter cube is in the denominator. So let's come here. Let's multiply. So these are the number of particles. Let's copy it from here to here. And I think these are little more. Let me check to my solution 132. Okay. Okay, so we have multiplied the value of Ri, which we now do not need to do for now. 3 times Mi C3, and then we divided by this one. It's going to be 5. Ni value is going too high. So let's remove this 1000 from here. We keep all the values as given here. So, okay, we'll get these values for the value of Ni, the number of particles. Okay, then as we move on to determine Ri, we will be multiplying. As we move on to determine Ri, we will be use multiplying this Ri equation as we see here, Ri into 4 e and I to the power 1 minus alpha upon 6. So let's see, Ri multiply, let's bracket. In the denominator we have 4 times e value as 4 multiply by ni value, that's going to be g3 to the power 1 minus alpha value. It should be here. Log this one also. Numerator is closed. Let's, in the denominator we only have 6. So let's close this one, and these are the values of Ri which will found here. To obtain the suction from the Ri, we can only do twice Ts upon. Like here, if you'll see, suction value is nothing but twice Ts upon Ri value. So here we can write 2 times the value of Ts is here. It's in uh, millinewton per meter. So we'll convert it to Newton, maybe kilonewton. So we'll multiply 1 e minus 6, and then we'll have divided it by Ri value, that's in mm. So we'll multiply Ri H3 into 1 e minus 3. These are the suction values which we'll obtain here. I think there's some problem with that. So let's see. We obtained Ri value is 0.014132, and these values are correct. But while determining Ri, we are having some trouble. So let's cross check this one. Maybe we'll copy this formula directly to this place. And the value of suction 2. Okay, so now these values of suction we have obtained, and you might need to cross check some of the formulations in Excel. And if we plot the particle size distribution, that is percentage final versus particle size, then you'll obtain this curve. And if you obtain plot the SWCC curve, that is suction, the theta I, the volumetric water content versus the suction value, then you'll obtain this curve. So you'll see these two curves, they are related to each other. If the if this one is for a well-graded soil, then this one will also behave like a curve of a well-graded soil. So it will have a large range of suction values, right, up to 10,000. So up to 10 kPs. And let's move on to our slide here. So this is the problem which we were solving. And here if you'll see from RFRS method, that if for a fine grained soil, that is the particle size is lesser, then for this one it will be looking like a uniform fire. It will be suction values will be very high and within a very small range. And for a well-graded soil which is having a large range of particles, then for that suction value will also range for a larger section. For a gap-graded soil that's having a bump here, for this one you'll have a bump in suction values also. Okay. So these two are basically related. That and the RMA method is a very good method to obtain soil water characteristic from the data of this particle size distribution. Okay. So now we have discussed about the RFIDs method. We have solved one numerical in Excel. Okay. And I'll be uploading that Excel so that you can cross check if there is any error in that one, and you can also solve for yourself. So coming to the assignment of week 6, the first one is that water content versus time data is it asks that water content versus time data, theta versus time data is the only input parameter required in RDTC software for fitting the SWCC of soil. So if you see in RDTC software, retention of data, then it requires you to provide pressure versus theta value, the water content and the value of suction or the pressure values. Okay, not the time. Therefore, that is not the only data that is required, only input parameter required for RETC software. Okay, so you can solve it accordingly. Also, from here you can see Brook-Coren Van method that to determine the soil water characteristic curve, you will need the values of suction also, so that you can better fit these results, right? Psi B, etc. And the RETC software is a gradient-based optimization algorithm for fitting the SWCC data style. That is correct. RETC uses gradient-based optimization, and it also has some neural network part that you need to explore. And then we have the third question that says the prediction of SWCC from particle size distribution using RFRS method is most suitable for clays. So the answer to that is that basically, so initially the soil is in dry state, and when you saturate the soil sample or the water content increases, the white ratio remains the same. That is assumed in this method. So the white ratio should not change. Okay. So that is the assumption made in other Paris method. So generally, this is applicable for coarse-grained soil like sandy, loam, etc. So this method is mostly suitable for coarse-grained soil. Okay. So not the place, not most suitable for clays. It can be used for clays, but it is not most suitable. And then the fourth question is the modeling of the flow through soil and drain filtration require SWCC data only. So as we have seen earlier, that if for the infiltration problem, if we need to require to model it, then from the SWCC data, we can obtain the fitting parameters or the fitted curve or prediction curve. Then from there we can obtain using statistical method related to hydraulic conductivity symmetric suction, and then we can model the infiltration problem. So this statement is said to be correct. Okay. Then we have the estimation of SWCC from particle size distribution curve requires the information of bulk density of soil. So here we go on to the RFLS method. Then if you see here that do we need the bulk density? Then yes, we need the bulk density at a particular point. Okay, so using a particle require information of the bulk density of soil, but this bulk density can be calculated for unit volume as 1 upon rho d. Okay. So with this, this is the content for week 6, and for one more class that we have left for week 4, we'll meet again on Sunday. So if you people have any question, please do let me know, or else or you can mail me also later on if you find that you have any question. Okay, so I'll wait here for a while. You can just go through what I've taught, and you can let me know if you have any question. So as we do not have any question till now, I'll just close this meeting and we can meet again on Sunday to discuss more problems for week 4. And thank you very much for joining.